Alright, good morning again. So we were looking at the last of the controlled sources, and that was the current controlled voltage source. So last class we did that in a hurry, so let's just quickly recap and then we can proceed. It was the current controlled voltage source. Okay, and today is what? March 10th. This is, I think, the 32nd lecture, if I am not wrong. Okay, so what was the current control voltage source expected to do? It was supposed to take in a current, right, multiply it with some quantity, we are just calling that Rx because it has dimensions of resistance, and give us the output voltage V out. Okay, so we said that this essentially means that we can ensure using a feedback loop that V out minus I in times Rx, this quantity must be 0, correct? Alright, so we wanted V out minus I in Rx to be 0. How did we achieve this? Basically, we had a rail which was the V naught rail, right? We said that was your V naught or V out, correct? And then we, using this, we basically created this difference because you have I in flowing through Rx, correct? This voltage here would essentially become Vx, correct? Which is your, we can call this Vx, and I can say Vx is V out minus I in Rx, right? And then I have to use this voltage to control V out. Now, because our MOSFET is not a voltage controlled voltage source, but it's rather a voltage controlled current source, the way you can change V out is by either pulling out current from V out or pumping in current into V out. So we decided that we will connect a current source here, right? That current source is a variable current source, and I call that I1, and I said that should be proportional to Vx, or rather, yeah, that should be proportional to Vx. How does this work? Should be proportional to Vx or minus Vx? No, it is very important to fix that sign, because that was the sign determines whether you are in a negative feedback loop or a positive feedback loop. Okay, so assume that, okay, so we don't know whether this is plus or minus, right? So you are doubtful of whether it's plus or minus. So let us take the minus case and do the analysis. All right. Now, what is your Vx? Vx is V out minus I in Rx. Okay. Assume that say Vx is greater than 0. What does that mean? It means you have to decrease V out. Okay. What will happen if I1 is proportional to minus Vx? You are going to pump in current into V out, right? If I1 is proportional to minus Vx, implies V out will increase if Vx is positive, correct? So does that solve our problem? It does not solve our problem, correct? So all of this means guys, I1 must be proportional to plus Vx. Okay, so you can just go over around the loop and you can find out, you know, what is it that you require. So this should be plus Vx. All right. Now, what do you do with this? You have to make you have to replace something here with a transistor, right? So how do you replace that? So the way it is drawn, it's fairly clear, no? Remember, all of these are incremental quantities, right? So let me draw a box, and then as usual you can tell me how that box will become.
Shouldn't we take the direction of any current source, because if we take I1 proportional to Vx,
Okay.
then according to KCL, then that node doesn't follow that.
Which one?
But if that node of Vout,
Ah,
both are coming out.
that's okay.
But if then it means something that should be negative.
That's correct.
If we will take that to be negative,
It will all work. It will work. You can see that. That is, if you flip your I in, okay, if I in instead of being down were pointing up, then this V out will be what?
we have Vx plus.
Yes, but in that case, what do you want your V out to be? In that case, you will not want V out to be equal to Rx times I in. You will want it to be minus Rx times I in. Okay, so you just change what, it's a current controlled voltage source, right? So you can introduce a negative sign in the final expression that you want. In fact, we will do that. When we do the analysis of the full circuit, we will actually toggle the I in direction, because we usually want the current to go into your amplifier, right? So you will get a negative sign in the output. Which arrow? This arrow. This arrow is the fact that it's a controllable source. I am saying that I1 is proportional to Vx, no? It's a controlled source, that's all. Huh? Exactly. Now we will make that triangle thing. Okay. So how do I make this into the MOSFET circuit? Let me first have everything else as it is. So that is I in, that is Rx. Okay. Now what should happen? How should the MOSFET come? Right? So I can make this thing as the gate, right? And then I can have, as he pointed out, we can have the triangle there, not the triangle, this diamond, right? And then what? Nothing else. That will be your V out. And where's your drain, source and gate now? So this is the drain, that is the source, and that is the gate. Okay, all right. So this is your incremental circuit. Now if I want to replace this thing with the MOSFET itself, how will that look? This is essentially identical to, right? And what do I do here? I just can replace it with my MOS. Okay, so this is my incremental circuit. Okay, when I so we can figure that out now. Okay, we'll figure that out. All right. So this is your incremental circuit. We now have to make the full circuit based on the incremental circuit. So as the question Ishita is asking, you want the V out here, right? Which means, what is the restriction? What does this essentially say? The one main take home from this, or rather, what is the constraint on the biasing circuit that this incremental circuit imposes? Correct. In other words, tell me with respect to whether the drain, gate and the source can be shorted or not. Right? What does this imply? This implies that in the full circuit, you cannot connect drain to what? Drain will not be connected to ground, to any voltage source. Because if it is connected to any voltage source, what will happen? In the incremental circuit, that drain will become ground, and then it will trouble you here, right? Because you are going to take V out from the drain in the incremental circuit. Okay, so given that, which bias circuit should you use? Right, that's why I started today's class by asking you to have a look at that particular circuit. Okay, so which kind of bias circuit do you want to use? Drain feedback, because in the drain feedback circuit, what will happen? So if just consider the drain feedback biasing. Consider drain feedback biasing. How does that look? I have my transistor, then I have my Iref there, right? So I am drawing only the bias circuit, right? And then I can take this and connect it here, right? This will work, correct? However, we figured out that for certain applications it's okay if it's required that we have some kind of resistance here. Let us not say that is large and small and all of that, right? We'll just call that as some R, let me call that Ry. Okay, the presence of that Ry does not hurt you at all, because exactly, because no current flows through the gate. So the presence of that Ry does not hurt you in the biasing circuit. It can help you in the incremental circuit. Okay, so this is your drain feedback biasing, and I have my incremental circuit like this. So can I put the two together, and can you construct the full circuit based on these two? Okay, that is your drain feedback biasing. Let me call this as this is my Rx, this is my incremental circuit. Okay, now using these two, can you construct my full circuit? All of you draw it. So the full circuit is very straightforward to draw, right? You have your amplifier there, correct? And this should be ground. On top you are going to have your Iref there, correct? Now you want to take V out from the drain, so basically you capacitively couple V out, and then I want a load resistance, so I connect my RL there, correct? Next, what do I want? On the input side, I am going to have this resistance here, which is my Rx, and then this is going to be my I in. Where is? No, Ry is any resistor in that drain bias circuit. Now it so happens that Rx becomes your Ry. I did not want to draw, you could, Rx is Ry basically. Only thing is, in the, when you, sorry? But IN is a small signal circuit, is a small signal source. Correct? So in the when you are making the incremental circuit, what will happen? This would be VDD, right? So in the incremental when you are making the incremental circuit, what will happen? Iref will disappear, correct? Capacitor will become short, and all of these things will remain as it is. It will give you what you want, right? So that is your full circuit. All of you get this? Any questions? Which current source? I? But that's what you want, no? It's a current controlled current source. A current control voltage source. So your input is a current. That's the incremental current, correct. Okay, now that we have this, what do? You draw again the incremental circuit for this, including any other complication that might have come because of the biasing, and then do a small signal analysis on that and work out what is your gain, what is R in, what is R out. Okay, very straightforward. So let's do that. So how will this look? Now what I am going to do is that here drawn this way, I out is basically I in is the source, right? Is your signal source. You'd want, let's assume that we want that current to go into the device. So we'll just we'll flip this direction. Does not matter. You'll just introduce a minus sign in your V out. Okay. So now we want V out to be equal to minus I in times Rx. Alright, because we have flipped the direction of I in, V out direction also flips. Okay. Okay. Now if you want to draw the incremental circuit for this, how will it look? I have my GM times what? VGS. This is to ground. Then I have my I in. Also, in addition, let me assume that this I in is not a perfect source, so it has a source resistance associated with it. So I have I in going into RS, correct, and that will give me my VG, and then what happens? VG is connected via Rx to VD, right? So you have an Rx over here, and then what else? You have your RL. Alright, now I want you to find out the various quantities. So this is my V out, this is I in, okay, and then I want to calculate what is my input resistance R in and what is my output resistance R out. Okay, now in this particular case, when I am calculating my R in, let's assume that you want to include the effect of RL also. As I said earlier, it depends. Okay, sometimes people include RL when they are calculating R in, sometimes they don't. In an exam, if I give it, I will mention specifically include or don't include. Okay, in this case we are going to include the effect of RL also while calculating R in. In fact, I am not going to calculate R in here because this particular circuit, does it look familiar to you? Huh? Y parameter? No. Just think carefully. How did we start the class today? So right? So this is essentially looks identical to your common source amplifier with drain feedback, because you can replace this I in RS as what? You can replace this guy as a with a VS and an RS, right? And if you make it a voltage source, you put a capacitor also, so that there's no issues. Okay, so if you do this whole thing will look identical to your common source amplifier with drain feedback, and we have done that again earlier. But what is the difference? How can the same circuit work as a common source amplifier and also as a current controlled voltage source? When we did that design of the common source amplifier with drain feedback, we finally imposed the condition on the value of what was Rx, right? The equivalent of Rx. We had called it RDG there many weeks ago, right? So what you will find is that we'll get expressions now. In order that final expression looks like what we want for this particular application, the condition on this Rx will change. So you will get an expression with a numerator and a denominator. If you make one thing the dominant term, it will give you the common source amplifier. If you make something else the dominant term in that expression, you will get this current controlled voltage source, and we will see that. Okay. So now what I am going to do is to ask you to go and look at your notes for this particular thing and tell me what is the value of the various quantities that are there. So looking into what you have already done for the common source amplifier with drain feedback, you can write down R in, R out and the gain. Okay, R in is going to be Rx plus RL divided by 1 plus GM RL. R out we had derived earlier as Rx plus Rs divided by 1 plus GM Rs. Okay, and V out by I in, right? You can work this out and this will become minus. It's a slightly messy expression, but I'll leave it at that. You can check that this is indeed correct. We have already done it in a slightly different form earlier. Divided by GM Rs RL plus RL plus Rx plus Rs. Okay. Now we have these expressions, right? How do you know I didn't just bluff and write some nonsense here? Okay, so you take some limiting case and let's see that the limiting case all makes sense, and then we'll come back to these expressions. So let's take the limiting case. We'll take the limiting case of what? Which one? Oh, sorry. Rn is looking in from here. Good question. This is Rn. So let me correct it on the previous page also, that that is R. Okay. Now in the limit of things going to infinity and 0 and all of that, okay, let's say that my Rs tends to infinity. Okay, then what else do you want to send to infinity? Okay, and also let's assume that my GM tends to infinity. Okay, and let's see what happens. So what will Rin become now? If GM tends to infinity, this will become 0. Okay, what will R out become? 0. Okay, what is V out by V in? Or V out by I in? So how do you deal with this? You basically divide by all the quantities which go to infinity. So what are the quantities going to infinity? GM and Rs. So you divide by GM Rs. So you will get minus. What will happen? You will get RL Rx minus. What will this term become? RL by GM, and the denominator you will have, the first term will become RL, next term plus RL by GM Rs plus whatever, this Rx by GM Rs plus 1 by GM. Okay, now you know whatever is going to infinity. So because these two are going to infinity, that becomes 0, this becomes 0, 0, 0. Correct? So this becomes equal to minus Rx, which is essentially what you wanted. So this messy expression does become what you want. Okay. Now we work with the situation where you have a finite. Can you justify why this Rin is 0? So when Gm is infinity, right, what did you write here when you discussed the feedback loop, right? You said Vx was V out minus I in Rx, correct? And Vx is the potential on top of this current source. When Gm is infinity, what happens to this V out minus I in Rx? It goes to 0, which means Vx is 0, right, when Gm is infinity. So with that in mind, you come back down, Vx is this terminal, right? Now that became the gate, right? So when you come down another page, effectively that is this terminal, right? So this was that Vx, right? So what this is telling you is that in the limit of Gm tends to infinity, this Vg is 0. So whatever current you pump in, the voltage here is 0. So what is the input impedance? That voltage divided by this current, and that is 0. So that's why your Rn is 0. Similarly, what about your R out? So you go back to your R out. Okay, R out is basically looking in from this side, right? R out will be looking in from here. So assume that you pump in some current into this, right? And then this thing goes up a little bit, this voltage. So if or rather, yeah, you apply a test source. So say you increase this thing by some delta V. What will happen? This current will, or rather this voltage will also go up by delta V. Then what will happen? Because this voltage has gone up, this current, right, will go down, or rather the current magnitude will go up, the direction is down, right? So this current will go up by how much? Now Gm is infinity, so it will go up by, it will really give it a big kick, and it will compensate this delta V. So irrespective of what delta V you put in, all the current will be supplied by this I in itself. So you will not have any current that's required. So your resistance again is going to be 0. Okay. Or rather, you look at it the other way around. If you pump in some current, the voltage change will be 0, right? That's easier. No, don't look at it as giving a voltage and then your current going up. That will complicate you. Apply a current so that the voltage goes up by delta V, and the whole feedback loop basically kills the delta V. So your resistance is nothing but delta V by I, and that will be 0. Okay. Anyway, that little bit which I mentioned now, you can think about it. It's not really, it's just to justify that whatever we had makes sense. Did everyone follow what I last said? Lot of blank faces. Yes or no? I somehow think it is no. Let's just okay. We were discussing what is the output impedance of this in the limit of Gm being infinity. This is Gm Vg, S is 0, so it's just Gm Vg, and I am saying Gm tends to infinity. Okay, so to calculate the output impedance looking in from here, what should I do? So I will put an I test here, and I want to find out what is this. Okay. So assume that this I test causes this thing to go to some delta V. Which one? And In should be killed, correct? Right? Because that's correct. You remove your In. Okay. So, but then what's happening? If you kill your In, what happens to Vg? No, it's correct. What we are doing is correct. So so you have put I test here, right? You have called this voltage delta V. What will Vg be? This current is 0, right? There is no current flowing now because you have removed there is nothing here. So this is floating. So this will also be delta V. So this is going to be Gm times delta V, correct? Gm times delta V. and GM is infinity. So I test will basically flow in here. So what is your delta V going to be equal to? Well, you can't really write out the voltage across around a voltage source. That's a little difficult. So it's better to just verbally say what will happen, right? So you have a delta V there, and any I test over here, because GM is infinity, right? With the delta V being 0, GM delta V can be finite to carry this I test. Basically all of this I test has to flow from here and go in here. No current can go there. So you can ensure that by having delta V 0 and GM infinity. So you will finally find that delta V is actually 0. Or you can include an R0 around this and then do the calculation, it will still become 0. That's easier. Okay. Just put an R0 and do the calculation. So that's why your R out would be equal to 0. Okay. This was just trying to justify what we got doing the exact calculation. Okay. So this is not very important. Alright. Let's quickly finish this off. I have these expressions. Essentially I want to look at the final expression, I don't need to look at the others. Look at this expression, and what do I want V out by IN to be? What do I want V out by IN to be? I want V out by IN to be minus Rx. Okay, now what should I do to these things in order to achieve that? So which is the term I should make dominant in the denominator? In the denominator I should make this quantity dominant. In the numerator what should I make dominant? I should make this quantity dominant. If I do that, what will happen? That by that will give you this. So you can write out now the condition that you require. What do you want? First condition for the denominator, GM RS RL must be greater than RL Rx and Rs. Okay, and from the numerator what do I want? Basically you can take out Rs RL common, then you will have GM Rx minus 1. So your GM Rx must be greater than 1. Okay. Now just to put this in perspective, for the common source amplifier with drain feedback, what were the corresponding conditions? So you had an RDG, which was your R large. That is the equivalent to your Rx, and we wanted that to be greater than GM Rs RL plus Rs, and we wanted GM RDG again to be greater than 1. Okay, so the main thing that is differing between these two is this condition. Correct? So just in the choice of your Rx, which is your feedback resistance, you can either make this work like a current source amplifier with drain feedback or a current controlled voltage source. Can you give some physical intuition into that? And then we'll close. You see, for the current controlled voltage source you actually want feedback, otherwise your V out will not become equal to IN times R. So when will you get feedback? When Rx is small or large? Think again. Basically when Rx is small you will get feedback. When Rx is large, take the infinite case. If Rx is very large, what will happen? This thing will disappear. If this disappears, right, your drain and source are no longer connected, there is no feedback. Right? So basically the difference between the common source amplifier with drain feedback and the current control voltage source is basically in the magnitude of this feedback. So if you have Rx being very large, and very large is defined again by whatever we derived earlier, right? then then the feedback is weak and it will only work like a common source amplifier. On the other hand, if Rx was small, which is what we are getting now, okay, you will get stronger feedback, and that will allow you to basically make a make the current controlled voltage source. Okay, and the magnitude of small and large and all of that are here, right? Because here you see Rx is less than something, so this is basically Rx being small. Okay. Now Rx is an input quantity that you already know, right? You want your V out to be Rx times In, which means that given a value of Rx, you have to choose everything else such that Rx appears to be small. In this case, RDG was your Rx, and that is going to be essentially large. Okay, so the same circuit can work as two different things based on the amount of feedback that you are introducing in the circuit. Alright, so that brings us to an end of all the 4 control sources. Very good. So the next topic we will start next week.